fair warning, I would like to have a small quiz on Wednesday on the stuff that we're going to see today and tomorrow-ish. It's going to be really small, probably about 2 questions, and a little bit of Newton's laws from before. And then I'd like to have a 2-part test next week, Tuesday, Wednesday. Is that cool? A multiple choice part and a free response part on the big dynamics chapter. That way, it's kind of also for review, is really how I'm doing it. That's how I'd like to do it. Is that all right with people?
So quiz on Wednesday.
So a small quiz on Wednesday. It's going to be on forces, but predominantly really what we're doing today and tomorrow. Predominantly, it's more of like, do you remember what we did today and tomorrow? And then next week on Tuesday and Wednesday, it'll be a little bit bigger, kind of more for reviewy stuff on dynamics as a whole. So the special forces, the application of Newton's laws, the ramp, tension.
So the test on Tuesday and Wednesday is stuff that we already.
Yes. Yeah. Cool. All right.
But
So
not tomorrow.
that's next week. Yeah, that's next week. And I'll give you guys kind of an outline of what to look for and what to see. I also have a homework to put up today about these types of questions that we're going to see moving forward. It's a little bit long. I'm going to make it due next week on Tuesday. Actually, can I make it due next week Monday so that you can come see me if you have questions?
But the homework on this wouldn't this apply to the quiz?
Yes.
So
I would recommend to do it earlier. You don't have to do all of them. They're not very long. It's not very long. I'm going to make it due next week Monday so that you can have time to come see me before the test. That way, I want to do it Tuesday and Wednesday so that my office hours on Monday after school, you could still come and see and ask questions.
Wait. Physics homework due Monday? Is that what you said? Next Monday. Monday? Yes.
Yeah.
Is that already posted on?
No, it will be. I have it written out, but I haven't had a chance to put it up. So I'll put it up at lunch. So I kind of I skipped through this before because from all the stuff that I saw on the curriculum, it really wasn't huge. But then I went to this workshop, and somebody made a comment in passing about how there isn't a whole lot of places for calculus to kind of show up. And one of the easiest places is this. And I went, okay, well, we should probably do this problem. We really should. Just so that we all kind of see the calculus so that it doesn't come out of left field and freaks us out. So I have the video. I can show the video with you. So imagine that I had an object that was starting from rest, up somewhere in the atmosphere, up high, and I'm going to drop it so that it is free-falling down. But in this case, we're not going to ignore air resistance.
Yes. Oh, never mind.
Oh, okay. Well, welcome back. So we're not going to ignore air resistance. In this case, we're going to assume that air resistance is a velocity-dependent force. And as we saw, I think it was, right here, a velocity-dependent, frictional force kind of looks like negative BV. The negative is really just to say that it's going in the opposite direction of your velocity. Right? Does that make sense? So if I'm moving down, the resisting force would be pushing me up. Right? That's really all it's saying. So don't get too caught up on the negative for the equation. The negative is going to be really helpful to help us figure out direction, especially on the free body diagram. That B, that's a coefficient. It could be a bunch of things. We don't have to worry about it just yet. All right?
So the negative is saying
the negative is giving me direction. It's just telling me that it's resisting V. Whichever way V goes, that force goes in the opposite direction. So let's do 2 things first. Let's figure out an expression for the terminal velocity. Where'd green go? Here it is. Everything was 100% perfect. There we go.
This is all about drag?
Yes. Drag or velocity-dependent friction forces. I think drag is better. It's a better name. So the first thing we're going to do is find that terminal velocity. And then the second thing we're going to do is find equations for velocity, acceleration, and graph them. It would be really useful to know what these things look like. We kind of should have an intuitive idea of what the velocity and the acceleration should do, especially if we understand what terminal velocity means, but it would be good to have proof, evidence. Where's your notebook? You just got it.
I lost it.
How?
I thought
Oh my god. Oh my god. I'm gonna get you one of those chain wallets, but instead of a wallet, it'll be a notebook. A chain notebook. You had a question?
Yeah. So terminal velocity, it's like, is it the point where the velocity is great, no longer changes, or how do we quantify?
So terminal velocity. When you can no longer speed up. Terminal, the final velocity you get to. It's the fastest you can go. Because what happens? Physically, think about it. What happens as this thing is falling? Air resistance is pushing this up. And if it depends on velocity, as I go down, the acceleration of gravity is doing what to my object? Yes, but what else physically? What's it doing to it? No.
Wait, say that again?
It's decreasing.
The acceleration is doing what to this object as it comes down?
Making it speed up.
Speeding it up. It's speeding it up, which means its velocity is increasing. But if it has this velocity-dependent friction force, as it's speeding up, that velocity-dependent friction force is also, I'm going to say increasing, right?
The opposite
It will be increasing. So that means that the rate at which this thing is going to speed up is going to do what?
Wait, if the rate at which it speeds up is the rate at which it gets air
Don't you
resistance.
reference?
So this part here, does this guy change?
The air resistance
No.
the same as gravity?
No.
No. Well, that's what I'm getting to. But just to build conceptually, as this thing is falling, that vector, this is a decent free body diagram, so I'm going to stick with this for now. That vector stays the same because its mass doesn't change, and the acceleration of gravity, I mean, it changes in the decimal places, but not really. So this guy stays the same. But this depends on velocity. So as gravity does its thing, as the acceleration makes this thing speed up, this vector originally started really, 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 really small. And then gravity sped it up. So that vector got a little bit bigger. And then gravity sped it up. And that vector got even bigger. Which means the net of this is doing what as time goes on?
No, it's
The net force here is doing what?
they're not equal.
They equal each other to some to zero.
Which means it's going to approach zero. The net force here approaches zero. Given enough time, gravity is going to speed this up fast enough so that this velocity-dependent friction force gets big enough to equalize this mg. And then when that happens, what happens to the net force?
Zero.
It's zero. What happens to the net acceleration?
Zero.
It's zero, which means this system can no longer
Change velocity. Or change
speed up. It can no longer speed up, which means this velocity-dependent friction force is stuck. It's stuck wherever it's at.
Why can't it no longer speed up?
Because when this is big enough, it will balance out.
Wait, so what's B? Like,
Some coefficient.
we
A
don't
number.
care about it.
No.
So we just solve in terms of B.
Yeah, for now. Yes. So, for that first part, finding VT, we just said when that happens.
when the sum of
When they
forces-
equal out. So,
Like, isn't it just B equals mg over B? Like,
oh, we can't, you're jumping ahead, man. Let's start from basic principle. So, our sum of forces, give me what? I'm going to make my life really easy. And I'm going to say moving down is positive. Just make my life super easy.
So mg minus.
mg
Way to write the record.
plus, I'm going to say it should be minus, but I'm always very picky with the sigma because sigma means sum. It does.
Right.
And in this case, my minuses don't come because I'm subtracting things for no reason. They come because these things are negative vectors, because they have negative directions. And I want to make sure that if anyone comes behind me to look at my work afterwards, they'll be able to go, that was a negative vector. I see why that's subtracted. Can you go straight to minus? Yeah, go for it. But this is why I do it. So minus, I can go straight ahead and just call it BV, right? Equals what? 0.
And we would call what would you call that? FR?
FR, force resistance or force friction, whatever you would like.
What's the right way in a free body diagram to label positive and negative?
On the free body diagram, normally you do not. That is why I did not put this on the free body diagram. I put it right next to it.
Like, what's the right way?
If you look, for example, on my work, I have a little arrow right next to it pointing down with a plus sign, just like I kind of did there.
And the little key, that little Y down thing at the upper right-hand corner of the picture?
Here?
No.
Oh, yeah, okay. So that's another way of doing it. I actually did not even see that. I'm not going to lie, I did not see that. That's another way of doing it. That Y, the positive Y goes down.
Can you go to the previous slide for a moment? Just because I guess that's the...
This is the general form for a velocity-dependent friction force. Sometimes you're going to see that the coefficient in front is a little bit heavier. They'll give you more stuff. But like a coefficient divided by another coefficient times another coefficient, why can't you just turn that into one coefficient? You see what I'm saying? That's often what we do in physics.
Is the R resisting?
Resisting, or sometimes some people go friction. I've seen some people do that. Yeah, I would do it as resistance, but I have legitimately seen some PhD faculty members call it friction, and I was like, all right, man, whatever.
R is friction.
Yeah, I've seen it happen. So okay, all right, that's cool. That's cool, man. Force friction. You're a pickle now, Riction. All right. Oh, Morty. So let's solve for V. But now here I'm being really picky. Here we got to be really careful because here, what I should have written and what this is implying, but is not saying, is that my resistive force as a function of time depends on my velocity as a function of time. That's really what this is saying. Because as my problem goes on, that V value changes, right? Until it reaches this maximum value of terminal velocity, which is what I'm getting to. Because when I make this statement, that V is no longer a function. That V is a very definite number, 100%.
So does that turn into German?
Yes. It really usually we won't say V max. Usually we'll say V terminal in this particular case.
Oh, just in this case.
Yeah, in this particular case.
You're allowed to say
Yeah. Yeah.
It only equals 0 because you're finding the terminal.
Yes. That only happens at that one point where those two vectors balance out. Not like that. That never balances. This balances. All right. So I'm going to move these around. I'm going to add it to the other side. I'm going to divide by B. And I'm going to get that mg divided by b equals velocity. Oh, vt. Yeah, thank you. Vt. So I have an expression for v terminal, velocity terminal. That's cool. All they got to do is give me what that b value is, and then I'm chilling. That's okay. All right. So I did part 1. That's not a big deal. Part 2. Now is when things are going to get a little trickier. Because what I'd like to be able to find is the velocity of this thing at any time, right? A very common question that I've seen, and I've looked up this particular question, and it comes up in a couple of practice exams that I've seen. They'll say find the velocity when it's 5 seconds into its fall. Find the velocity when it's halfway, to its maximum VT or to V terminal. Sorry, I was going to say V max, and I should not have. But so we would like to be able to find a function for VT. So we're going to start back up here. This was all for part A. We're going to start.
Is there a difference?
It is trickier. We're going to start with velocity for a reason. I'm going to show you why in a second. And in order to do this, I'm actually going to go to the next slide so that we have it nicely organized because it's involved. I wanted to make sure that I had it all worked out so that I didn't have to rely on me memorizing the whole thing. So we're going to start with what we know. We're going to start with that free body diagram. mg minus bv equals ma, right? That's what Newton says in general. And until this reaches V terminal, right? This is actually kind of an implicit v function, right? It depends on time. And if I wanted to find a function for that, I could say, well, this equals m dv dt, right? That's really what a is. A is dv dt. This is the reason why I want to start with v, because I've already got that v guy over here chilling, and I can split up my variables nicely. So let's rewrite what this looks like. mg minus bv m dv dt. Now I can't cancel out my m's. And that's the thing that we normally would like to do. Why can't I do that?
Positional and
Yeah, that BV guy, that bovine dude, does not have an m term, so I can't cancel out the m's. What I could do is kind of simplify my life a little bit and divide by m and only keep it here with the v. I could do that. And if I do that, it'll look like g minus okay, that's a little bit prettier, a little tiny bit prettier. Now what I'd like to do is split up my variables. I want anybody that's a v to be with dv. I want anybody that's a t to be with dt. And I want them on separate sides so that I can integrate them. Okay? So I'm going to move this dt from the bottom here, from the denominator, to the numerator on this side. Does any of these guys have a t? No? So I'm going to move those guys over here to dv, because that has a v. All right? The g doesn't, but I'm going to move everybody together. It's a constant. It's totally cool. And moving just this guy by himself is going to suck.
No, you can't.
Yeah.
You can't separate variables with addition and subtraction.
Yeah.
Don't we already have like a physics formula that gives us acceleration given like velocity final and initial? Like why do we have to go through this whole calculus?
You're going to see why. Because it's not the same thing. And the reason is because of this BB thing. That BB thing makes things really ugly for us. Pretty ugly for us. We did something very similar to this before. Like super similar with the mortar problem. But we're going to do a slight different thing with it. I'm going to show you, because it's really useful to do one little change to make this graphable. So I'm going to split this up, and it's going to give me dt equals I multiplied dt to both sides, so but then I divided okay? Now we're going to integrate. I'm going to integrate from the beginning of my problem, happened when? Time t equal 0. 2 time t equals t. And my velocity, I did say that it started from rest. So my velocity is from 0 to some value b. No, some value t, and then I could plug in whenever I want. I could plug in whatever time that I want into my function.
Does it matter?
Here's what matter.
If you put BT or
Calculus.
No, it's not calculus healthy,
No,
but it's physics healthy. That's all that matters to me.
you can't put the same variable in the differential and the upper limit.
Well, if you would prefer,
Yeah, well,
if you would prefer, I'll call it v prime, the velocity that it will get to at that time t.
isn't it the same if you write BT?
V sub t?
Yeah. No, because the v in the equation is like a function. V of t. V is
So instead I'll call this
value.
vf, the velocity that it gets to at that time t.
Why can't you
TF?
write BT
If you want, but
if you leave it without that, then it's a variable. It's the same variable you're integrating with respect to, and you can't integrate it.
okay. Physics is not that clean.
Yeah,
I
but
guess.
I don't want to.
Yeah, that makes sense. All right, so let's do the easy part on the left. The integral of dt is t. Okay, that's not bad. T. That one on the right is gross.
Don't you need the
Yeah, wouldn't it be T final?
Yeah. That one on the right is gross. What would I need to do to solve that one on the right? A u sub. A u sub would be great. What would I set as u?
minus b over
And then du would be negative b
B over M.
dv, right? So I could replace this ugliness with, I'm going to ignore my limits of integration because I'm just going to substitute right back. So I'm going to be cool with that. Now, in order to do this, I actually need a negative m over b, right?
And the outside.
On the outside. Because what I'm doing is substituting in dv. But I need, from this, I'm going to replace dv with negative m over b du. But that negative m over b is a constant, and I'm going to throw that out to the front. This should be pretty easy to integrate. ln. I'm not going to change my limits. I'm just going to go right back. So this is going to give me ln. So this will be t equals negative m over b times ln of g minus b over m v evaluated between 0 and v. V active, yeah.
That's the value.
Yeah. Wouldn't it be outside?
That's the value of g minus b over m. Well, here.
This number is never going to be bigger than that number.
Right.
And we already know that from the first part. The first part of the question, it can never be bigger physically.
Are you recording this whole thing?
Yep. Okay, so now let's evaluate this thing in here. Let's do that. Okay?
Let me take it
Okay, so little issue there. Here, put it. No. Let's evaluate what.
I just want to evaluate this part here. I've got to do the v final part in here, and then I've got to do the 0 part in here. Because unfortunately, that 0 part does not cancel out. Usually, it does, and it's nice when it does, but in this case it does not. So I need to make sure that I get some stuff out of this, right? I can't just ignore the 0. It does not go away. What's up, David?
Every time you do an integral, you always have to put an evaluation.
Yep, between the top limit and the bottom limit. So top minus bottom. So I'm going to take care of this guy. Remember that it's all going to be multiplied by negative m over b, okay? But I'm just going to kind of do it inside of here. So evaluating the top part, that's going to be ln of g minus b over m v final minus the 0 part, and then that 0 part, this is going to cancel, and it's going to leave me with ln of g. Now that looks gross, except we have some properties of logs. The differences of logs is the ratio of logs. So this is going to turn into ln of this stuff
over.
divided by g.
And then.
So I'm going to write that out over here. So that's going to give me t final equals negative m over b ln of g minus m over b v final over g.
That's B over.
Oh, sorry, I flipped it. Thank you. Okay. I'm almost there. What I wanted was a function of v. But that's not what I have. That's not what I have. I have a function that gives me t. All right, cool. So what do I have to do? Inverse it. All I got to do is inverse it. Right?
So negative
Yeah, whatever.
over M. Why inverse it?
Because I want to solve for v. That's what I want. but I don't have v equals something. I want to make it v equals something. So let's make it v equals something, right? So let's first take care of this guy. Let's multiply this by negative b over m. Let me just check to see, do I have the next page? Yes!
Wait, can you go back to the second part?
Quick calculus question. When you plug in that, you know that evaluation symbol, how do you know which variable to plug in that v final for? Like, here it's kind of obvious that if you plug it in for velocity.
It's the independent
But, like,
variable
yeah.
in that part of in that integral.
But there's a bunch of other variables.
Yeah, but that's a constant, that's a constant, that's a constant, that's the only variable.
Oh.
And to be fair, that's also the variable that I just integrated. I integrated by v, dv. So I'm going to plug in for v.
Oh, so you just
Okay.
There's no way to mathematically to know like constant variables.
Well, I mean, I know that g is a constant. I know that m is a constant, it's mass, and b was given to me as a constant. So yeah. Can we go? All right. So I got TF equals negative. Was it m on top or b on top? M on top. M over b ln g minus b over m v final all over g. So all I did was rewrite it. Now I'm going to solve for v final. I'm going to first take care of this coefficient in front by multiplying by the reciprocal. So that's going to give me TF right?
Or you could
Okay? Everybody with me right now so far? Just really easy, basic step, baby step. Okay? Then, how do I get rid of this ln? I can take the exponential, e. So e okay? Now what? Multiply both sides by g. I'm going to do a little couple steps because at this point it's really just algebra, right? So multiply by g, subtract this guy over here, and then so this will turn into, and I just want the last part, really, it's all I really want. Okay. That'll turn into something that looks like that after I factor out a g, right? And then I have this b over m thing in the front. Now, a couple things to note. If t gets really big, if I give this thing enough time, what happens to this part of the function? What happens to this? It does approach something. What does e to the negative t approach when t gets really big? 0. This approaches 0. So as t starts approaching infinity, as it gets really big, this whole thing here goes to 0.
You don't know the t approaches.
So it's the opposite.
No, I'm saying that as t gets bigger, as time goes on, this number starts getting closer and closer to 0.
Okay.
Right? I could, but I mean, it's math.
You don't know the time. Like,
And that's yes, but that's not the point that I want to say this in physics. And I guess I will say it as a limit, but I want to say it all together as physics. So as time gets really big, as time goes on, right? Because time's not going backwards, first of all. Time's going forward. But there's a negative right in front of this thing.
Yeah.
So this exponential function is actually getting closer and closer to negative infinity as time goes on. This guy drops off, goes to 0. Which means, what does v final approach? Ho! Ho!
But you don't know that T approaches infinity.
T doesn't have to get to infinity. The point is, as T gets big, that's what this is saying. As T gets bigger, from 1 second to 2 seconds to 3 seconds to 4 seconds to 5 seconds, those numbers are getting bigger. So as T gets bigger, that number gets so much smaller that it goes essentially to zero.
Yeah, but for the first two values.
Yeah, but it's the graph.
I know, this is not saying what happens at the first few values. This is saying as T approaches infinity, as it gets bigger and bigger, this part of the function
So shouldn't you write
Terminal velocity as it approaches.
approaches zero.
so shouldn't it be like Vt is equal to mg over v as if t is a number?
So if I wanted to write this as a limit, I would say the limit of v final as T approaches infinity is the terminal, because this guy goes to zero.
Yeah, that makes a lot of
So now to find the acceleration if velocity is not determined.
Actually, I could probably keep writing this a little bit more. So
Yeah, that's what else we're like. No. We already had that. So
Yeah, but now for if velocity is not in terms of t now,
that's my point.
then your assumption is just zero.
Wasn't the point of it to solve your
isn't that what you just said? Didn't we not say that originally? That Vt, terminal velocity, happens when your acceleration goes to zero.
So
That
this
is
is
true.
just to prove it.
Well, now I've got an equation. Not only that, I've proven what V terminal is. That's not the important part. The important part is I now have an equation that is going to tell me what my value for velocity is at any given time. That's useful. On top of that, actually, this equation is graphable. It's totally graphable.
Yeah, but shouldn't it be like piecewise or something? I don't see how
We
it.
literally graphed this last period.
So, what will this function do? What will it look like? We should have an idea of what it should do. What should this function do? Big picture. What should it do?
What do you mean what should?
What should the velocities do?
It's increase. Well, no, it should approach zero as
Whoa, no. If it approaches zero, that means this thing is
terminal.
no
Approach terminal.
approaching rest. How is it approaching rest if it's approaching zero?
It should decrease because it's
So there should be a value, V terminal,
where this look is
that it approaches. It should approach that value. That's called an asymptote. So it'll approach that asymptotically, yes. But this function, and it's actually negative, so it's whatever. So it'll look like this. Something more or less like that. Doesn't actually start at zero, but something more or less like. The important part is that you understand that this is not linear. It shouldn't be linear because the accelerations are.
So it's a heavily transformed e to the x.
Yes.
Negative.
It shouldn't be linear because the accelerations are changing. But it is approaching this value asymptotically. And the acceleration, my homework to you, and I want you guys, I'm going to pick somebody tomorrow to come up to the front and solve it. Find me the acceleration function and the graph of the acceleration function of this guy.
So it would be.
I don't think I would integrate. I would anti-integrate. No, anti-integratiate. That's what you do after Thanksgiving. when you already got your gifts and you don't want to suck up to grandma no more, you anti-ingratiate yourself. Well, this was a really ugly integral. That's why I wanted to do it together, so that if you see it, it does not come out of left field. And to be fair, it's not an ugly integral. It's a U sub.
You just have to keep track of what's a variable allowed.
Yes, it's a U sub. It's really not that bad.
I live by that.
By
I live by that one. I just read it. Like,